So we're going to start the next session, which is about CO2 capture using membrane-based technologies from Dr. Asim Khan. Asim, maybe you could introduce yourself at the beginning of the talk. Okay, the floor is yours. Thanks, Asim.
Thank you, Dr. Chanpai. First of all, thanks to International Association of Carbon Capture for organizing this session, and especially to Dr. Chanpai, who is doing a really tremendous and great efforts in promoting carbon capture, which obviously is really the need of today's and myself, I am Asim, and I'm currently affiliated with the Department of Chemical Engineering at COMSATS University. It is located in the city of Lahore in Pakistan. You can see my email address to reach out. And currently, since last 2 months, I am in IU Madinah, which is a university in Medina in Kingdom of Saudi Arabia. And I'm working here as a visiting professor here, doing certain tasks, and my current affiliation, that's why I put both affiliations here. So this, since it is a training session, and I believe most of the participants who are here and who will be listening to this recorded talk as well later on, are early career researchers, probably many are students, many have interest in carbon capture. So that's why I have tried to keep my talk more, or this training about carbon capture, CO2 capture using membrane technologies, to more into basic concepts. So the people who are not familiar with carbon capture using membrane technologies would be able to understand the basics and fundamentals. And later on, I have tried to include some case studies so they can analyze how membrane technologies are playing a role in CO2 capture. A little introduction about our research group. We call it Membrane Systems Research Group at COI. COI stands for COMSATS University, Islamabad. We established this research group in 2013, so it's been more than a decade. I'm leading the research group, also founded the research group, and we started with carbon capture using membrane technologies, but more recently we have started to increase the focus and the applications. So now we are working on biofuels upgradation. A lot of effort is being done on water and wastewater treatment. We are working on fouling control, surface treatment of membranes. So everything, all the activities revolve around membrane fabrication, membrane characterization, and application of membranes. And here you can see membranecoi.com, our website of our research group. If you want to reach out, if you want to know more about our activities, you can always write to us. Now, coming to the outline of this training session on membrane technology, I will start with a quick background. Already in the morning, we have had talks on absorption and adsorption. So I have been editing my talk in a way that I don't repeat most of the stuff. That's why I kind of removed the pre, post, and the different capturing processes of carbon capture. I will give a brief introduction to membrane technology, and then I will move to how the membranes are made, how they are synthesized for CO2 capture. I will talk a little bit about transport mechanisms, what are the challenges that are faced by researchers and for industrialists who want to adopt the technology of carbon capture based membrane based carbon capture. And then in the end, I will give some case studies how we as a researcher or our research group is tackling those challenges that are faced by membrane technologies. And my conclusions will be more about future directions and some comments how we foresee membrane technologies in the years to come. And since it is a training session, so I have tried to put in the session learning outcomes. What I expect after this session, the participants will be able to, I expect they would be able to understand the concept of membrane technology, specifically for CO2 capture. They would be able to know the fabrication techniques for CO2 capture. They will gain insights into the transport mechanisms through which membranes made for carbon capture operate. They would be able to identify what are the recent challenges by membrane technology. And finally, through the case studies, they would be able to analyze and apply the fundamentals for different CO2 capture scenarios. So this is in the next hour, I will try to cover these learning outcomes for this session. Now, coming to a little bit of background, when we talk about CO2 or carbon capture or climate change or global warming, used to be a couple of decades ago when I was in my undergrads, it used to be an invisible phenomena. It used to be a futuristic or prediction that scientists used to make, but not anymore. Now I'm coming from Pakistan, a country in South Asia, and we see the effect of probably we are the one of the worst countries affected by climate change. We have seen droughts in front of ourselves. We have seen one of the huge floods in the history of the country in the past decade or so. We have a huge mountain range called Karakoram and Himalaya, where we have huge glaciers, five of the top 8,000 meters mountain ranges. And we have seen huge melting of glaciers leading to floods, droughts, and we do see the effect of climate changes. And when we see the numbers, they are staggering. If you look at the latest reports by different international agencies, we do see staggering numbers. 2023, we are right now in the last month of this year, and it is already on course to be the warmest on record. We have seen 6% rise in CO2 emissions than what was emitted in 2015. I have put 2015 because this was the year when we had Paris Agreement, where we committed to decrease the CO2 emissions and to limit the global temperature rise to 1.5 degrees to pre-industrial levels. But the numbers show something else. Already the emissions have increased in the year 2023 by more than 1.1%, which is higher than the average of the last decade. And it is estimated that there is 50% chance that global warming will increase the set level of 1.5 years in only 7 years. So all these staggering numbers, all these figures give us only one direction, that we need to do more and more, whether it comes to policy, whether it comes to carbon capture, whether it comes to moving to renewables. But when we look at the numbers of different gases and emissions, we see the most staggering number, the highest number when it comes to greenhouse gases is for CO2, which still accounts for about 65% of global greenhouse gas emissions. And when it comes to CO2, it's mainly fossil fuels, different industrial process, and to meet the energy demands. So carbon capture and storage, CCUS, is probably one of the key areas where we need to do research, where we need to drive policy, and where we need to do more and more application and industrialization if we are to come up with solutions to restrict global warming and to restrict climate change in the years to come. When we talk about carbon capture, there are many different technologies. There were already sessions about absorption and adsorption this afternoon or this morning. And each of these technologies have their merits and their demerits. Each has their challenges. But we think that if we are to work towards a sustainable future with technologies for carbon capture, probably one of the technology cannot do everything. Depending on the source, depending on the composition of the gas mixture that contains carbon dioxide, it has to be a mix of different technologies. And membrane technology, again, is one of the very promising technology because of the many different merits that this technology has. It is a simple technology, involves, when you compare with the other techniques, competing techniques, it has low capital cost for a membrane technology plant. It is a very scalable plant. If you see the global CO2 carbon capture plant, you see that they are much compact than the other competing technologies. A membrane, when it is produced at a lab scale, it is relatively easy to upscale it at an industrial or a pilot scale level, and membranes are stable at higher pressure. Most of the times, polymeric membranes are used, which are stable at high temperature and pressure. In fact, they need high pressures to have higher driving force so that we can minimize the cost to run the plant. However, just like any other technology, it also has certain challenges that need to be overcome if we really want uh, to commercialize this technology and to reduce the cost of carbon capture. I will talk about few of these challenges in the slide.
Sorry, Asim, I think it's muted now. Can you unmute? It happened also.
All
No, it's
right.
muted.
Yeah,
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 good. Yeah,
I pressed it again. So it's fine
yeah.
now. So my membrane is a semi-permeable selective barrier that lets some particles, some fluids to pass through, and it restricts the ones that we want not to pass through the membrane. It carries out separation. Generally, when we think about membrane, we think about it as a filter that separates on the basis of size. But that is not only always true. In fact, in case of CO2 capture membranes, they separate not generally not on the basis of size, but on the basis.
Sorry, Asim, it's muted again.
I don't know why it is happening.
Maybe I should, yeah, you can start. Sorry for that.
I hope it works well because I am on the presentation, so the microphone is not accessible. So I hope it works fine now. So the separation takes place on the basis of size, solubility, and there are also charge membrane that separate on the basis of charge differences. And in order to drive flux through the membrane, we need a driving force. The driving force, depending on the application, can be of various different kinds. For gas separation, generally the driving force is pressure difference between the feed side and the permeate side. But in some cases, this driving force can be a charge difference, concentration difference, and temperature difference as well. When it comes to this technology, when we compare it with other technologies, it is relatively new separation technologies, and we have seen more and more application of membrane technology in the past couple of decades. So there are many application of membranes. Even when we talk about gas separation, there is hydrogen separation, CO2 separation, syngas upgradation, natural gas separation, biogas separation, and these different separation processes through membrane have different principles on which they operate. The transport mechanisms are different, the problems or challenges are different, but in all these different applications, there is one thing that is common, that is they all use membranes. When we talk about the comparison of different membranes, let's say we have different manufacturers who are synthesizing membranes. There are two ways by which we correlate the performance or efficiency of the membrane. One is flow, flux, permeation, permeability, permeates, all of it, you will see they have different units, but all of it means how much of the selected material is coming out of the permeate side of the membrane. The other efficiency parameter is selectivity, retention, rejection, or separation factor. They have different units, they are different formulas, but all of them means how much selective is the membrane and what is the purity of the product that we get out of the membrane. If we talk a little bit about the history of this technology, it is a long history of more than 100 years, and the first application was in water treatment, but it was in late 50s when in medical application, in kidney dialysis, membranes were produced, that really the membrane market started to grow. If we talk about CO2 capture and gas separation, it was in early 1980s when hydrogen recovery, membranes for hydrogen recovery were produced, and we have seen more and more applications, including nanofiltration, reverse osmosis in the last years, fuel cells, membrane distillation, forward osmosis, and so on. But for gas separation membrane, the real breakthrough was made in 1960s by Loeb and Suryanjan. Before that, the major issue was that there was a trade-off between the membrane stability, membrane separation, and the flux that was coming out of the membrane. And the reason is that membrane technology, it is a mass transfer, it is dominant mechanism for flux or permeation through membranes. Generally, it is said that a membrane should be about 200 to 250 micrometer thick so that it can bear high pressure, it can be mechanically stable enough. But the mass transfer, if you know the Fick's law, it says thicker the membrane, the less is the flux that comes out of the membrane, and we need more and more driving force, we need more and more energy that we have to give in order to drive the flux out of the membrane. So before the membranes that were developed by Loeb and Suryanjan, they were thick enough, and as a result the permeation or the flux from the membrane were really small. What Loeb and Suryanjan did, they made a membrane in a way that the membrane had a porous sublayer, as you can see here, which is about 50 to 200 micrometer. But as you can see, there are huge amount of cylindrical pores in the membrane or finger-like pores in the membrane. Through these pores, we will have very less resistance to the flux, but this 200 micrometer thick membrane would provide us huge mechanical stability. The separation or the main resistance to the flow comes from the very thin top layer, which is less than sometimes even 0.5 micrometer. So the resistance to the flux or the main thickness to the flux comes from only 0.5 micrometer, and the rest of 200 or 250 micrometer only provides us the mechanical stability. And once these asymmetric membranes that has these two layers, a bottom, a sub layer, and a top thin layer were produced, a huge amount of research started, and then we started to see more and more application of membranes for CO2 capture, for other applications, because as mankind, as researchers, we were able to develop membrane that had mechanical integrity as well as high flux. And this is the reason over the years we have seen huge potential and increase in membrane gas separation market. Right now, it used to be few $1 million. Now, right now in 2020, it has reached and surpassed $1 billion globally, and it is increasing at the rate of 7.5 annually, and it is predicted to increase to 1.4 billion US dollars in only 5 years time. So you see huge increase, and the reason is so many different applications, but one of the major application of membrane market is carbon capture. The classification of membranes can be in a different way. We can classify membranes on the basis of their origin. Generally, the membranes that are used commercially are synthetically produced. They can be classified on the basis of composition. Membranes can be
你回来你
organic.
不学习啊？你光玩了。
They can be inorganic membranes, and sometimes they can be a mix of
明天啥？
organic and inorganic. And the membranes can
这是简
also
单
be
啊。
classified on the basis of morphology. So
嗯，
membrane, how they look like,
你不要玩时间
cross-section
太
wise,
长
for
啊。
example. So membranes can be
几点
porous
节约啊？你知
or
道
they
吗？
can be dense. Membranes, so the entire morphology or the cross-section of the membrane is porous or it is dense. They can also be asymmetric. So for example, they can have different type of pores. They can have a porous sublayer and a non-porous thin skin layer at the top, or they can be composite comprising of two different materials a sub-layer material comprising of a different material, and a top layer comprising of a different material. When it comes to membrane materials, generally two types of materials are used for membranes. They are either polymeric or non-polymeric. Each type of material has their advantages and disadvantages. When it comes to polymeric membranes, the membrane market for carbon capture is mainly dominated by polymeric membranes. These membranes are extremely cheap when it comes to non-polymeric, for example, ceramics, metal, glass, these type of membranes. Polymers are generally very easy to process to a membrane form. They are easy to scale up from a lab scale to pilot or industrial scale. However, the major issue with the commercialization of polymeric membranes is that the flux and separation are generally low. On the other hand, non-polymeric materials or membranes, these possess high chemical and thermal stability. In comparison to polymeric materials, they show very high fluxes and separation because generally the separation is on the basis of size in case of non-polymeric material, while in case of polymeric material, the separation is generally by solubility. I will talk about it later when I will talk about the transport mechanisms. But the main challenge with these materials is that they are extremely expensive when it comes to comparing with polymeric material. Also, when it comes to processability into the form of a membrane, they are extremely difficult to process and lead to brittleness and defects in membranes, and their long-term stability is generally low because of this reason. Now, I will talk a little bit about the different membrane fabrication techniques, how we make membranes, how we synthesize membranes. And as I mentioned previously, since there are so many different type of membrane materials, since there are so many different type of membrane morphology, I already talked about it in the membrane classification part. So it is very difficult to name one, two, three, or even four, five different techniques that are generally used for membrane fabrication. Depending on the morphology that we want to obtain, depending on the material that we are subjecting to, that we are processing to a membrane form, we select the membrane fabrication technique accordingly. I will talk about a couple of techniques that are generally used at an industrial scale to fabricate membranes, but it is considered that phase inversion is a universal membrane fabrication technique, and through this process, through this fabrication technique, we can make membrane for any given application and for any given morphology. This is the reason I will talk about this universal membrane fabrication technique in a little bit more detail. So phase inversion is a process in which a polymer is transformed from a liquid to a solid state in a controlled manner. In the process of phase inversion, both kinetics and thermodynamics play an important role. As I mentioned in the previous slide, we can generally make all type of membrane morphologies for every type of membrane application, whether it is liquid or gas separation or CO2 separation. We can use this technique. So what happens in case of phase inversion? We generally polymers are solids, so we use an appropriate solvent to make a solution. We call it dope solution, casting solution, or a polymeric solution. Then by using thin blades, we cast this membrane into a form of a thin film, and then we immerse it in a non-solvent bath or a coagulation bath. Non-solvent means the solvent in which our polymer does not dissolve or has negligible solubility. As a result, inversion of phases takes place, and we get from a liquid phase to a solid film. I will show you in the by a small video how this process takes place at a lab scale. So here we have a substrate, and here we have polymeric solutions. and you will see through this device we cast this liquid film into thin liquid films, and then after certain time of evaporation, where evaporation of solvent takes place, they are immersed in a non-solvent. In this case, water is the non-solvent in this example. And once again, non-solvent means solvent where our polymer has negligible solubility. And as a result, solidification of the polymer takes place. And we have films. Here we can see 4 different films of a certain polymer. This example is for polyamide, and then we use these membranes for application. So in case of phase inversion, generally what happens, as you saw in the video as well, we have a polymeric solution and then it is immersed in a non-solvent bath. As a result, mass transfer takes place. The solvent, because it has because there is a concentration difference between the film that is being immersed. So as a result, solvent diffuses into the water while non-solvent diffuses towards the film. Because of the exchange between the solvent and non-solvent, there a demixing takes place. Solvent comes out of the membrane, non-solvent diffuses into the membrane, and if we control this entire process, we can end up with a porous membrane, an extremely porous membrane, membranes with finger-like structures, membrane with spongy structures. So we can make membranes of different morphologies, different configurations, different porosities, depending on which type of polymer we are using, what is the concentration of polymer we are using in the solvent, what is the exchange rate between the solvent and non-solvent. So if you can see here, there are 14 different very common parameters that we can control in phase inversion. What is the polymer that we use? What is the molecular weight distribution of polymer? What is the solvent that we are using in the dope solution? Are we using any additive? What is the concentration of polymer in a casting solution? What is the substrate material? And there are so many different parameters. And as membrane researchers, we optimize these 14 different parameters to come up with a morphology that we want to obtain for any given application. I will try to give you a couple of examples of how we control these parameters of phase inversion process and we end up with different membranes. So here, as you can see in the figure, we have used isopropanol as a non-solvent and dimethyl acetamide is used for a polyether sulfone polymer as a solvent. And as you see, here you can see the effect of polymer concentration.
And sorry, Asim, I don't know what happened. I think you are muted again. Maybe someone else clicked.
I don't know, maybe someone doesn't like my
It's fine now.
presentation.
Yeah, I think because
And
thanks.
all right. So back again, and here you can see as we increase the polymer concentration, the top layer thickness keeps on increasing because now there is a polymer rich phase, and when it is immersed in the non-solvent bath, the polymer solidifies here, and here it is solidifying even more, here even more. As a result, we are having a more and more thicker top layer with a porous sublayer. Here it is again another example, and you can see as the polymer concentration is increasing, we are getting more and more thicker top layer. Another example is effect of non-solvent. It is a very interesting example. You can see here on the left we have isopropanol as a non-solvent in the coagulation bath. On the right we have water. Isopropane water mixes better, has more miscibility with dimethyl acetamide, which was used in the casting solution. Since it has more affinity, so water diffuses very quickly in the membrane matrix. DMA very quickly comes out. As a result, water because of the very fast or instantaneous demixing of this solvent and non-solvent, we have pores that are generated everywhere. In case of isopropanol, it does not have very high affinity with dimethylacetamide. As a result, the exchange between isopropanol and dimethylacetamide is slow. As a result, the polymer tries to solidify, and by the time isopropanol reaches the top layer of the polymer, we have solidification at the top layer, resulting in asymmetric structure. Another example where we used evaporation time. So the time after we cast the membrane, we let the solvent evaporate. The more time we provide the solvent to evaporate, we see thicker and thicker top layers. And at the last, I would like to give an example of co-solvent. So what is done in this case, we use two solvents. One is a non-volatile solvent, for example, dimethylacetamide, and then we add some portion of a very volatile solvent, for example, tetrahydrofuran. When we add the non-solvent, what happens? After we cast the film, the co-solvent, the volatile co-solvent tries to very quickly evaporate. Since it evaporates, it leaves behind very thick and very highly polymer rich region behind. And as a result, the more and more co-solvent is added, we see thicker top layer, and here we see very high concentration of co-solvent. As it evaporates, it leaves behind thicker polymer rich zones, leading to, here we can see almost half of the membrane is non-porous and half of the membrane is porous, because all of the co-solvent evaporates, leading to such structures. The same phase inversion technique is used for making membranes for carbon capture and industrial scale, but just like the equipment that I showed you a couple of slides before, here we have much larger scales of these baths. So we have the polymer solutions that are made in tanks, straight tank reactors, and then they are passed through these roller blades in the non-solvent path, and finally the membrane is produced, as you can.
I think maybe this time is because of the internet connection. I think.
Yes, sir. Your internet is interrupted.
Who is? I think it's not question time.
Sir Asim, we can.
At the top of this
Okay.
porous.
Asim, can you hear me? I think.
Okay, can you hear me now?
Yeah, it's good. I think we lost you in a past minute.
Okay. I'm sorry for the connection. Not under my control. All right. So moving on to the next, the last fabrication technique that I want to talk about. It's a very common technique, widely used at industrial level. It is called interfacial polymerization. In case of interfacial polymerization, again, we take a substrate that is produced generally by phase inversion, and then it is immersed. The interfacial polymerization is carried out by using two different monomers. Generally, a diamine or a acyl chloride is used to produce a polyamide. So these two monomers react very rapidly at a room temperature when they come in contact. Generally, what is done, an aqueous solution of diamine is immersed in the pores of the film. Then it is exposed to the organic solution of an acyl chloride. At the interface, these two monomers interact and polymerize, and leading to very thin films at the top. Here, let me show you from a quick video how this process takes place. So again, it is a lab example, but also takes place at the industrial level. So this white film is the substrate that is being taped using an adhesive, and it is produced by phase inversion. Now, as a first step, we will use this diamine aqueous solution, and we will spread it throughout the substrate. We will remove excess by a rubber roller. And finally, at the last step, we will immerse it, or we will immerse the organic solution, in this case hexane and trimethyl chloride. At the interface of these two solutions, abrupt polymerization takes place, and after we carry out washing and drying, and as a result, all of the solvent is gone, and what's left behind is a thin top layer. And these membranes that have two different type of materials, a porous substrate of a different polymer and a top layer of a different polymer, are called as composite membranes. Now moving to the membrane performance, as membrane engineers or scientists or chemists, we aim to make membranes that are highly permeable, that are highly selective, and that are highly robust. That is, the membranes that have high mechanical stability, high chemical stability, and a good lifetime. So an ideal and most optimal membrane is the one that shows very high permeability, very high selectivity, and has a long lifetime. In order to achieve this criteria of highly permeable, highly selective, and a robust membrane, it is important to look at the transport mechanisms through which we control the permeability, selectivity, and robustness of the membrane. Generally, for CO2 permeation, there are three different dominant transport mechanisms. Either it is Knudsen diffusion, in which the molecules collide with the walls of the pores and pass through. It can be molecular sievings, where we have the pore size in between the size of the different molecules that are permeating through. So we get kind of a sieving at a molecular level. But the most dominant mechanism for CO2 capturing membrane is solution diffusion. Solution diffusion is a three-step process. In the first step, because of the high. So I was talking about the solution diffusion mechanism, which is a three-step process. In the first step, the permeating molecules are absorbed, then they pass through the thickness of the membrane, they diffuse through the thickness of the membrane, because these are generally polymeric membranes that have free volume inside, and they are always rotating around their axis and mobile. And then on the downstream side, we have just a second. So on the downstream side, they are desorbed, because generally we have a pressure difference or a driving force between the feed side and the permeate side. The solution diffusion mechanism, since it is driven by both sorption or solubility as well as diffusion that takes place between the feed and the permeate side, so we have to be very careful when we are predicting the permeability. The solubility of, when we talk about gases, they are generally very low in polymers. However, when we talk about CO2, it is a highly condensable gas. So when we select the material for permeation of CO2, we think about, or we select the material that has high solubility for carbon and for CO2. The diffusion, on the other hand, depends on the size of the permeating molecule. And that's why the flux that we finally get from the membrane, it is driven by both solubility and diffusion, and it also is inversely proportional to the thickness of the membrane. Thicker the membrane, lesser will be the mass transfer, and it is also depending on the driving force, the pressure difference between the feed side and the permeate side. This is the reason we have high pressure and compression on the feed side and vacuum pump on the downstream side, so that we can have more and more flux out of the membrane using a very small area of the membrane. And as you can see in this graph, it does not always mean that the smallest molecule will have the highest permeability of or flux. We can see here in this graph, on the x-axis is the diameter of the permeating molecule. On the y-axis, we have primary y-axis, we have the diffusion coefficient. On the secondary y-axis, we have the sorption or solubility coefficient. And as we can see, definitely the diffusion falls as the size of the permeating molecules is decreasing. The sorption increases as the size of the permeating molecule is increasing, but this is not the case for permeability. For different polymers, as you can see this experimental data, the smaller molecules are not always the most highly permeable molecules. The reason is that we have to look whether the permeation is driven by diffusion or solubility. So it is not always the case that small molecules are highly permeable, even though small molecules can have very high diffusion coefficient. If we talk about the design of membrane modules for industrial carbon captures, generally there are two types of modules that are used on industrial scale for CO2 capture. It is either flat sheet membranes. I showed you one example in the video where a flat sheet membrane was being made, but it can also be tubular membranes. And depending on the diameter, they are classified as, if they have diameter more than 10 millimeter, they are classified as tubular. Capillary membranes are the ones which have diameter between 0.5 and 10 millimeter, whereas the most common type of membrane module designed for carbon capture are hollow fiber membranes that have diameter of less than 0.5 millimeter. Smaller the diameter, the smaller the radius of the tube, higher is the area per volume ratio of the membrane. And as we know, the membrane plants are generally very and extremely compact plants as compared to the competing technologies. And this is the reason why hollow fiber membranes are generally preferred. However, there are many other criteria on the basis of which the selection of module is made, depending on the mixture, depending on the cleaning, maintenance, compactness, scale of the separation, and the lifetime of the membrane. Now, talking about the different type of modules, the flat sheet membranes for carbon captures are generally of two types. Either flat sheet membranes are made and then they are framed in a plate and frame module configuration, or most commonly it is used very less for CO2 capture, this type of application module configuration. For CO2 capture, generally spiral wound membrane configuration is used, in which the flat sheet membranes are rolled, and in between each roll we have spacers and we have a central feed line, and the permeation through each configuration is collected in a central permeate line and then collected in the header. This is an example of an industrial scale spiral wound module. The other type of membrane module is hollow fiber membrane module, which is produced by phase inversion. So what happens is we have a jet through which the polymer solution is sprayed. It goes into the non-solvent bath where it solidifies, and as a result, these hollow fibers are produced, which are hollow from inside. And the configuration can be that we can send the feed from outside in, or it can also be sent through the hollow part of the hollow fiber, and then it permeates outside. And we can have thousands of these hollow fibers potted together through epoxy resins. So as a result, hollow fiber membrane modules are extremely compact and can deal with extreme large volumes of carbon dioxide and can separate in a very small facility. Now, finally, I want to talk about what challenges, what problem, and what issues the membrane researchers face, and why membrane research is not able to fully commercialize when it comes to carbon capture. One of the major issues with this technology or the challenge that is faced by membrane technology is this trade-off between permeability. Here, the example is for CO2 permeability and separation for a natural gas. So on the y-axis, we have selectivity. So it is selectivity, how a membrane is selective for CO2 in comparison to methane. Here, we can see the different type and variety of polymers, and for each polymer the permeability and selectivity is plotted. And if we can see from this graph was first plotted by Robinson in way back in 1991, but over the years different plots have been plotted, and as we can see that there is an upper bound, that is the membranes that are highly permeable, they are less selective, or the membranes that are highly selective are less permeable. So what it means that for each type of material there is a trade-off between selectivity and permeability, and it is said that if membranes have to find their way into market, if we want to reduce the cost, if we want to handle large volume of membranes in a very large volume of gases in a very small area of the membrane, we have to make membranes, come up with membranes that have permeability and selectivity beyond this upper bound. And we can have a membrane in this region by having highly permeable and at the same time highly selective membrane. So this is one of the challenge for membrane researchers to come up with membranes that overcome this trade-off between permeability and selectivity. The other major challenge is membrane plasticization. As solution diffusion is the major dominant transport mechanisms, so because CO2 is highly condensable gas, what it does, it dissolves into the polymer matrices, it disrupts the chain packing, it increases the free volume. As a result, what happens? The permeability goes up because now there are more and more spaces and swelling of the matrix, so CO2 can definitely pass through. But because of the swelling of the matrix, because of the changes in the free volume, the non-desirable gas, for example, methane, nitrogen, or hydrogen, is also able to pass through, leading to reduced selectivity. So if I can sum up, there are two major challenges for membrane researchers to come up with membranes that do not have the trade-off between permeability and selectivity, and the membranes that are resistant to plasticization. So what are the future directions? I believe I have about 10 minutes to wind up. So I will quickly go through, give you some opinions about what the researchers are doing in case of membranes for CO2 capture. The current polymers, because they have limitation of trade-off, they are being modified, they are being functionalized, they are being treated in a way that they can have anti-plasticization properties, that they can have more affinity to CO2, so that we can have highly selective and permeable membranes. Another kind of strategy is mixed matrix membrane. Mixed matrix membranes are the membranes which combine the properties of polymer with non-polymeric materials, so that we have high separation of inorganic materials and high processability and low cost of the polymeric materials. Another type of strategy that is being used, ionic liquids, deep eutectic solvents, and different type of high CO2 affinity solvents are being used inside the polymer matrix, so that we can increase the selectivities and permeabilities. So I will talk a little bit about the mixed matrix membranes and give a little bit of what we have been doing in this field. So mixed matrix membranes are generally membranes in which low cost and easy processability of polymer are mixed with high selectivity and permeability of these inorganic materials. Over the years, zeolites, silica, ceramics, carbon nanotubes have been explored. More recently, MOFs and COFs, which are metal organic frameworks, and other materials have been used. But the problem with mixed matrix membranes is that because we are using a polymer which is organic, and inorganics like zeolite, silica, and CNT, which are inorganic because they don't really like each other. As a result, the inorganics tend to aggregate, or we have these interfacial voids between the polymer matrix and inorganic materials. And as a result of these interfacial voids, we have non-selective membranes that are produced because the non-desirable component can pass through. One of the ways that we see the future for these mixed matrix membranes is by using these metal organic frameworks, which are made by organic linkers, which are coordinated through metal ions to form this three-dimensional structure, which has really high surface areas. And because they are produced by these organic linkers, they can link better with the polymer as compared to other inorganic materials. Already we have seen in the literature that many different MOF-based membranes have showed performance beyond the upper bound. I will just give you a couple of examples. UIO66. So depending on the type of linker and the type of metal that is being used, we can make hundreds of different type of MOFs. So one of the example here, for example, is UIO66, which is a zirconium-based MOF, and terephthalic acid is used as an organic linker. It is an extremely chemically and thermally stable, and it has very good dispersion in various casting solvents, and it is relatively easy to make mixed matrix membranes out of it. In one of the studies, we functionalized it with sulfonic acid groups to increase the selectivity, to increase the affinity of CO2. I will just show you the results of what came out of it. In another study, MOF was used by carrying out modulation. So instead of post-functionalization, we used amine functionalization linkers. And as a result, we had the functional groups not only on the surface, but also inside the pores of the membranes. And another example, last example that I want to give you of why these MOFs have extremely high ability to bringing mixed matrix membranes into really commercialization phase. In this example, we used a biomorph in which we have a cobalt metal and adenine. It is called biomorph because adenine is the organic part linker in this case, and it has multiple Lewis basic sites, so it can interact with the CO2. CO2 can act as a Lewis acid, and by having this Lewis acid Lewis basic interactions, we can expect high absorptions. So here I just want to summarize how these metal organic frameworks are completely changing the landscape of mixed matrix membranes for carbon capture. We can see most of these MOFs are showing very high permeabilities and extremely high selectivities, and this is the upper bound for 2008. The last one was for 1991, and more recently there are more and more coming in, but still we can see that the MOFs are showing extremely high permeabilities and selectivities, and probably these are the materials for future if we want to overcome the trade-off. Finally, one study that I would like to mention how the researchers are tackling the plasticization or swelling problem that leads to lower selectivities. In one of the studies, we used sulfonated peak membranes. So monomers, we use sulfonated monomers, polymerize them into a sulfonated polyether ether ketone matrix. By carrying out this sulfonation, we were able to increase the glass transition temperature, and we were able to really rigidify the matrix to impart anti-plasticization properties. We were able to achieve very high permeabilities as we increase the degree of sulfonation, and at the same time the selectivities for CO2 and methane and CO2 and nitrogen were also increased. And it was very surprising results because of this sulfonation, we expected the polymer rigidity, which would lead to lesser permeabilities. But actually, if you see the trade-off doesn't exist, we see simultaneous increase in permeabilities for CO2 as well as selectivities. So we carried out the diffusion and solubility measurement, where we found out that the diffusion of CO2 definitely does increase. But because of these sulfonic acid polar groups, we were able to achieve much higher CO2 solubilities of the order of more than double when we increase the degree of sulfonation to 50%. And because the sorption and solubility increased to such drastic extent, it overcome the decrease in diffusion coefficient, leading to final increase in permeabilities. And the results also showed us, as we increase the pressure, this is the results for the membrane that has very low degree of sulfonation. You can see up to a certain pressure it is stable, and after that, after certain pressure, the permeability starts to go up because the membrane is being plasticized. There is increase in free volume, which is leading to increase in permeabilities. But in case of high degree of sulfonation, we can clearly see that the membranes were stable even up to 40, 45, 42 bar, which is relatively considerably higher pressure for a polymeric membrane. So this is one of the ways by which we can tackle the problem of plasticization for membranes. Finally, what's next for membrane-based carbon capture? There is a lot of research, huge amount of research that is being carried out in the area. A lot of work is going on by using mixed matrix membranes, membranes with modified polymers, with modified backbone structures, or modifying or functionalization of side chains. There are a lot of innovation that is going on when it comes to membrane fabrication technique. The membrane being produced at the lab scale level, it is one of the major challenge to scale up to pilot scale level, because most of the time, even in the commercial scale membranes, there is huge standard deviation of the coupons that are taken from one part of the membrane to even for a A4 sheet of membrane. So reproducibility is one of the major issue that is being faced for membrane researchers. Another major issue with membrane commercialization is because we need high driving forces for CO2 capture, so it leads to high energy intensity. We have to use high vacuums pumps, and on the feed side, we have to use high duty compressors. So the challenge is, maybe if we can integrate it, and already efforts are in place to integrate it with renewable energy sources so that the membrane process can be less energy intensive. Economic viability, and very important point, is to carry out life cycle assessment. Most of these synthetic polymers that are used for membrane manufacturing are produced by fossil fuels. So one has to think, on one side, we are reducing CO2 emissions by CO2 capture, but the polymers that are used, or the membrane manufacturing process itself, is highly energy intensive and leads to fossil fuel emissions. So we have to think about sustainable polymers, green polymers, converting waste into membranes so that we can move towards not only sustainable CO2 capture, but also the membrane manufacturing process is also made sustainable. And last but not the least, all of these technology, whether it is a membrane technologies, whether it is adsorption or adsorption, they will never succeed until globally, and not only locally, regionally, but also globally, there is a policy framework and there is incentives for carbon credits. And I hope that COP28 that is being carried out right now in these days in UAE, we come up with good resolutions that promote the technological development and research to come up with